Let us now consider the ground state properties of the electron gas. So we'll start with the Schrodinger equation, and we'll have to define the boundary conditions to solve the Schrodinger equation. The most natural way to do this is to assume that the electronic wave function cannot exist outside the solid. So if I consider a cube of length L, then you can consider standing wave like wave functions within the cube, and outside the cube the wave function will not exist. But since we are going to consider transport properties, we use a slightly different form of the boundary condition, and these are called the von Karman boundary conditions, where you think of a traveling wave and you assume that if I have a cross section of the solid like this, if the wave exists, if the wave exits at this point, it simultaneously re-enters at this point. So you have a traveling wave solution, and you don't have standing wave solutions. If the wave exits at this point, it simultaneously re-enters at this point. So this is 0 and this is at L. So you can consider boundary conditions such as these: psi of x comma y comma z plus L is equal to psi of x comma y comma z, and similarly for the other two dimensions. And those are called the von Karman boundary conditions. And it's a fairly trivial matter to show that that a wave function of this form satisfies the Schrodinger equation, and the energy would be given by this. But this is of course just the free particle wave function and the free particle energy that you may have studied in quantum mechanics before. Now, if I consider the momentum operator with the operator being minus I h cross del, then the wave function e power I k dot r gives the eigenvalue h cross k. So the momentum is equal to h cross k. The momentum of the electron is equal to h cross k. When I consider a lattice, this definition of the momentum will change, but for now it is just the standard momentum. We are considering a free electron. And I can also define the velocity as this. I can also think of this k as a wave number. I can have e power I k dot r, where it's a plane wave, and k dot r is basically k dot r is equal to constant is basically the wave front. So those are those represents the wave fronts that travel. And k will be given by 2 pi by lambda, and it's fairly simple to show that if I relate the k with the momentum as shown in the previous slide, you will get the de Broglie equation. Now if I impose the von Karman boundary conditions on the wave function, you can show that e power I k x L, e power I k y L, and e power I k z L should be equal to 1. This means that kx, ky, and kz are quantized in this fashion. Nx, ny, and nz are integers, that is, they can have 0 plus or minus 1, plus or minus 2, and so on. It's fairly simple to show that. You can just pause the video and show that in a moment. And if I take a two-dimensional space, k space, or if I have kx and ky in 2 dimensions, and if I plot all the allowed values of kx and ky, you will get a grid of points like this. And if I take a square of length 2 pi by L, then you can see that within this this square there is one allowed k point. So I can extend this into 3 dimensions and say, so I can have a cube of length 2 pi by L, and within that cube there will be one allowed k point. So I can draw this in 3 dimensions, and because the energy has a form, the free electron energy has a form given by this, where the k squared can be written as kx squared plus ky squared plus kz squared, then it can be represented in 3 dimensions in k space, and you will get a sphere. You will get a sphere representing that, and that sphere will be bounded at t equal to 0. The maximum value of the radius will be just will be corresponding to the Fermi level. So the surface of that sphere is called the Fermi surface, and you have all the allowed k k points inside. Although they are quantized, because the energy scales are very high, basically you can treat the energy distribution as a continuum, and you can integrate over the all allowed values of energy. So you need to find out the actual number of k points within that sphere. So to do that, we just said that a cube of length 2 pi by L in k space contains one allowed value of k. Now if I define some volume omega in k space, then the number of allowed values of k within this volume will be omega divided by 2 pi by L of whole cube. Now this is the maximum at t equal to 0. The maximum value of k will be kf, that corresponds to the Fermi level. So I can consider a sphere of radius kf, and so the number of allowed k points within this sphere of radius kf, that is within the Fermi surface, would be just given by this, where omega is now 4 pi by 3 kf cube, and I can now write that as that. But remember, I said that each allowed energy has got two k states, that is one for upspin and one for downspin. That is, each allowed k state is twofold degenerate. It can accommodate two spins, one upspin and one downspin. Therefore, the number of allowed k states would be multiplied by 2 to reflect that twofold degeneracy. So I have to multiply it by 2, and therefore this 1 by 6 will become 1 by 3. So now at t equal to 0, the total number of electrons is related to the total volume in this fashion, which is just follows from basically follows from here, because we have the total number of k states, and that essentially at t equal to 0 you can fill each of those k states with 2 electrons, so that gives you the total number of electrons. Each of those k states can be filled with 2 electrons. We have already taken into account that factor of 2, so that gives me the total number of electrons at t equal to 0 in terms of the volume V. Now I can define the n by V. I can write it in terms of small n, the number per unit volume. And remember, in the section on the Drude model, we had defined the space available per electron as 1 by small n, that is capital V by capital N. That is the space available per electron, which is 1 by small n, and we have written this as a sphere of radius Rs, and we have calculated this Rs, measured it, estimated it, and so on. So I can now rewrite the expression for kf in terms of this Rs, and I can also this gives me an estimate of kf, and I can now write the Fermi velocity in terms of the Fermi wave number, and I can also write the Fermi level, the energy of the Fermi level, EF, in terms of kf squared, and these are, so that allows me to estimate Vf and allows me to estimate EF and so on. So now immediately you can see that the velocity Vf is extremely high. It's like 1% of the speed of light, right? But it's like 1% of the speed of light, and this is complete contrast to the classical idea. In classical physics, the energy at t equal to 0 is 0. All the particles at t equal to 0 will have 0 energy. Therefore, the velocity of the particles at t equal to 0 will be 0 in the classical picture. We are looking at the situation at t equal to 0 with quantum statistics, that is Fermi-Dirac statistics, and we had just seen that all the levels up to the energy level EF will be filled, and therefore for electrons at the energy level, the velocity will be Vf, corresponding to the wave number kf, and that velocity will be extremely high. That's completely non-intuitive. I mean, you can never imagine that. Now these energy levels are so closely spaced that they will form a continuum. I don't want to get into the description of why it is a continuum. I will leave that to the Stat V course, but because these levels are so closely spaced, you can think of something called the density of states. That is, it is the number of states within a energy level dE. So the number of states dN within the energy level dE is called the density of states. So the number of states per unit volume n is given by this. We just seen this expression. So I can rewrite this k in terms of the energy as this using the free electronic energy expression. And I can now define the density of states G of E as dN by dE, and that gives me this. So in 3 dimensions, the density of states of a free electron gas scales as e power half. I would urge you to do this calculation for the density of states in 1 dimensions and 2 dimensions and so on. And it's quite simple to do this. Please show that the density of states can be written as 3n by 2e. Please show this. Now, I can write the number of particles per unit volume found within this energy segment dE as the density of states times the energy segment dE, G of E dE, which is dN, but I must also multiply it by the fractional occupation. That is, at t equal to 0, the fractional occupation f of E, that is the Fermi-Dirac distribution, will always be 1. So you don't need to explicitly multiply it at t equal to 0. But in general, if I want to find the number of particles per unit volume within that dE, then it will be the fractional occupation or the average number of particles for a given level E, that is f of E, into G of E into dE. That will be the general expression. And if I can integrate it over all possible values of E, I will get the total number of particles per unit volume. So then at t equal to 0, obviously f of E will always be 1. So I can just basically integrate G of E dE and I will get the total number of particles. Please integrate this and show that n is kf cubed by 3 pi squared. Similarly, I can now define the total energy of all electrons. This is also called the internal energy in thermodynamics or stat phi. We can use either U or capital E for this. We can also define the energy density as the total energy per unit volume. And if I want to find the energy density within the dE, then the most general expression will be the energy E into the fractional occupation f of E into dN. dN is basically G of E dE. So the number of particles dN into the fractional occupation into the energy E. Now the number of particles dN is basically G of E dE. So the energy density within the dE will be E times f of E into G of E dE. And if I integrate that over all possible values, I will get the total energy density. Again, at t equal to 0, the value of f of E, the fractional occupation, is basically 1. So I will immediately get a simpler form of this integral. Please do this integral and calculate u at t equal to 0 and show that you get this expression. E by n is 3 by 5 into Fermi level. It's a very simple integral to do. Please show this. Now you can estimate the Fermi temperature from these numbers from the Fermi level, and you can see the value of the Fermi level shown for some metals and the Fermi temperature and the value of Kf, Vf and so on. Look at the Fermi temperatures. The Fermi temperature is basically that temperature when most of the electrons are excited above the Fermi level. If you recall from the distribution, the Fermi-Dirac distribution, at room temperature there is not much difference from the step function that we saw. Only a fraction, very small fraction of electrons get excited above the Fermi level. But you have to heat those solids to 10 power 4k of that order of temperature, 10,000 Kelvin, to excite most of the electrons from below the Fermi level to above the Fermi level. So notice that the Fermi level is about 100 times more than room temperature, roughly, approximately. Now, given this information, you can also calculate the pressure that the electron gas exerts. The pressure is given as the derivative dE by dE, dE by dV, excuse me. This is from the standard from the standard first and second law of thermodynamics. You can show this. please calculate the pressure as 2 by 3 E by V. It's a very simple calculation to show. And also the compressibility can also be defined. The compressibility is defined as the rate at which the volume changes with pressure per unit volume, with a negative sign to show the that it's actually getting compressed. And the inverse of the compressibility is called the bulk modulus. And please show that the bulk modulus for the free electron gas is given by this. When I say please show, it means that these are all potential questions I can ask in the exams. I urge you to take this seriously and calculate it. These are trivial calculations. It will just take you 2 minutes to stop the video and do it. Then we look at the specific heat of the free electron gas. In the previous videos, we talked about a classical approach to this specific heat. We said that there are 3 degrees of freedom. If I just consider the kinetic energy, there are 3 degrees of freedom, X, Y, and Z. And each degree of freedom contributes half kT to the total energy. We call this as the equipartition theorem. So to the total energy, each degree contributes half kT. So I have n electrons, 3 degrees of freedom, and half kT. So that is my total energy. And the specific heat is defined as the rate at which the internal energy changes with temperature at constant volume. E is basically the internal energy, and I automatically get the classical value 3n by 2 kV. Now this value of specific heat for the free electron gas is completely wrong. It is wrong by a factor of about 100. That is, it's an overestimate by a factor of 100. At room temperatures, we are never able to calculate the specific heat contribution from electrons. Only the specific heat of the ions dominate at room temperature. Whether it is a metal or whether it is an insulator, you only get measure the specific heat of the ions at room temperature. Only at very low temperatures, the ionic contribution, that is, the ion means the lattice vibrations. The ionic contribution to the specific heat exponentially decays at low temperatures. So then the electronic specific heat dominates, and at low temperatures you are able to calculate the electronic specific heat, and that electronic specific heat scales as the temperature. It goes as T. Whereas the classical approach, it's a constant, and there is no temperature dependence at all. So it's a big failure. One of the biggest successes of the Fermi-Dirac statistics is the specific heat. That is, it is able to give you the order of magnitude correctly for the with respect to experimentally observed values, and it also gives you the temperature dependence correctly. Now the full calculation of the specific heat is quite laborious, and we cannot do it even in a normal StatV course. When I teach it, at least I don't do it. Maybe your teacher may do the full calculation, but there's a very simple hand waving way to arrive at the argument. I mean, to argue how the specific heat is calculated in Fermi-Dirac statistics. So the way to do it is, if you look at the Fermi-Dirac function, distribution function, we notice that only a very small fraction of electrons get excited out at any given temperature T. So you can argue that the fraction of excited electrons is approximately T by Tf. So at any given temperature T, the fraction of electrons excited is T by Tf into the total number of electrons. So when T equal to Tf, all the electrons will get excited. So that's a very simple idea. So at any given temperature T, the fraction of electrons is just T by Tf into N. Now you say that the internal energy is T by Tf into N into 3 into half kBT. So then the specific heat will now become, so now you can see that the internal energy picks up T squared. There's a T here and a T here, that T squared. So if I differentiate it, I will get T, and now I have the specific heat as 3n by 2 kB T by Tf. So the specific heat, there are two things here. One, the specific heat is now temperature dependent. It is linearly dependent on temperature, and the specific heat is reduced by this Tf, by a factor Tf. This factor Tf with respect to room temperature is it's 100 times more than the room temperature. So since it's 1 by Tf, the specific heat as defined by the Fermi-Dirac statistics is 100 times lower. That is why you are not able to measure it at room temperature. ionic contribution dominates so much that also the electronic contribution to specific heat is 100 times lower. Only at low temperatures you are able to measure this, and you are also able to verify that the specific heat indeed scales as temperature. This is the one of the biggest successes of the Fermi-Dirac statistics when applied to the free electron gas. So in the next video, we will talk about the Sommerfeld theory of conduction in metal. So we will take these ideas and apply it to different aspects of conduction we have studied before in the Drude model.